Thank you for the invitation, and sorry I changed the title. Yeah, that was a little bit confusing. Okay, all right. So yeah, thanks for having me. So I will consider a very classical question, I guess, for population genetics, which is the survival probability of a process. And so to make this point a little bit more rigorous, this question goes back to Benamé, Gordon, and Watson in the 19th century, which were interested in the extinction of nervous surnames in the early Victorian society. And they were seeing that they had less and less of these nervous surnames, and they were asking the question, is this due to the lack of offspring, and wanted to see what's the probability that they all go extinct at some point. And later in the beginning 20th century, all this has been made more precise, and made precise in the following way, which says for a classical, which we now call Gordon-Watson branching process, with an expectation which is just slightly above 1, so we will denote this by 1 plus some epsilon, and we will denote by pi the survival probability, then the following asymptotics holds that the probability of survival forever is asymptotically given as 2 epsilon over sigma squared, where sigma squared is the offspring variance. And this asymptotics holds as epsilon tends to 0. And this is by now also known as Haldane's formula, for example, and it's appeared a lot in the literature. And the question, which is also clear from the title we want to discuss today, is how does this asymptotics look like in a branching process in an IID random environment? So let me first define the object of a branching process in random environment. So we denote by P n0 the space of all probability measures on n0. So you can imagine your favorite offspring distribution you want to have, for example, Poisson, geometric, whatever you want. And a nice trick we will do here is if we take a probability measure f, which has this rather uncommon description f, we will identify the measure with its probability generating function, which we will denote for convenience with the same name. So just for your reminder, the probability generating function f of s is given as the sum where f with these square brackets denotes the probability mass of the distribution in Z. So this is the definition of the probability generating function. And what we now can do is we equip this space of probability measures with some metric, for example, the total variation metric. And this allows us to speak of random measures. So what we want to consider, so what will be a random environment for us? A random environment for us is the sequence V, which consists of a sequence of randomly chosen probability measures. So F1 is a probability measure, F2 is a probability measure, and so on. So we have the sequence of random probability measures, and in the same way as we can define for ordinary measures, the first and second factorial moment, which is just integrating the Z times the weight of Z, we can define this for these random environments. So remember that we picked a random measure randomly, and hence the first factorial moment, which is the offspring expectation in the end, this will be a random quantity right now. And in the same manner, the second factorial moment will also be a random quantity. But we will denote it in the same way as for classical generating functions, but instead we put this capital letter to indicate that this is a random object. And now let me define the main object of this talk, which is a branching process in IID random environment. And it works more or less the same as you are used to classical Gordon-Watson processes. We start with a single individual just for convenience. We could start with any number of individuals, but we will start with 1. And the next generation, Zn, is always compiled of Zn minus 1 times this Cin, which give the number of offspring of individual I in generation n. And now what's new now is that these Cin, they have the distribution Fn. So over the time of the generation, over the flow of time, the offspring distribution changes, and it changes in a random manner. So, but what we still assume is that given the offspring distribution Fn, all offsprings are sampled independently with this distribution. And to make the connection backwards, if you choose a very simple distribution, which means that Fn is almost surely some small f, then you just obtain a classical Gordon-Watson process back with offspring distribution f. And maybe the best stuff is definition by picture. So we start in the first generation, or the generation 0, with a single individual. Now what we do is we have our, oh, I forgot to mention that, and we are considering only V's where the F1, F2 are given by an independent raw. So there's no dependency between our environments, and obviously you can cook up a process where these F should depend on each other, which is, I guess, also a nice modification of this object, but we will consider independent ones. Okay, so in order to get the first generation, what we are doing now is, okay, we sample a random offspring distribution, which we will denote F1, and given that F1, we sample Xi11, which gives the number of offspring of the first individual. And now we just proceed in the same way. We sample the next offspring distribution, F2, again independently. And now given F2, we sample these three, for these three individuals here, their subsequent offsprings. And for example, now the environment was rather harsh to us, so we only get a few offspring. But it could be that in the next generation, the guys who remained, it's now a really good environment for them, which we sampled, and they can now branch more rapidly than before. So we get an extra source of randomness for these processes. We have this classical randomness known from Gordon-Watson processes just by the offspring distributions. But since we are changing the offspring distribution from time to time, we get some extra randomness into the model. And let me now come to the point which we want to look at is the following. We will now consider a sequence of branching processes in random environment, and they will be indexed by this capital N, which is just for convenience because we will have two sequences which will be important for us. And what we are now considering is the following case. I stated we want to deal with slightly supercritical processes. And in our sense, this will mean that the expectation of the random offspring expectation is 1 plus some epsilon n. So this is just as we have seen before for the Haldane asymptotics. But what's new now is that this random variable f prime of 1, which gives the expectation, can now randomly fluctuate between the generations. And we will denote the strength of these random fluctuations by nu n. So we have this new sequence nu n, which does not appear in the classical world of Gordon-Watson processes. And since we want to go to the critical value, we will let epsilon n tend to 0. And then the only meaningful way to obtain something nice is that also this nu n has to go to 0, because otherwise this random fluctuations in the offspring mean will just be way too big to observe anything nice. And lastly, what we also assume is that the variance of the offspring, so also the offspring distribution is also now indexed by n, and we assume that this is not fluctuating strongly. So we assume that there's some sigma squared, which is the general offspring variance, which is also converging to something nice. And okay, there are some more moment conditions which are not really insightful.
So
yeah.
My understanding now n is a parameter that is related to the generation, or
it's not right. Good question. It's not related to the generation. It's just a parameter that we can deal with these two sequences in the same way. So we can just let n tend to infinity, and depending on the ratio of these two guys, which will be in the next slide, we will see different behavior.
Okay, so it means that for any n, you have a certain branching process for which any generation is sampled as this f probability. So this f is a random variable with those expectations.
Right. And then we let the expectation go to 1 and the variance of this. Right. Yeah. Very good question to clarify. Yeah. Yeah.
Variance of psi n is an annealed variance, right?
Right.
So you are averaging over here.
Right. This is. Oh, sorry. Right. This is right. It's an annealed variance. do the total variance. All right, perfect. Let me state our main theorem. Oh, I forgot also, this is also all joint work with Gotts-Kersting from Frankfurt. And we are considering the same question. So we consider the probability of survival, which is now Pn. So this is also indexed by this capital N. And we will observe a phase transition in the following manner. So in the first case, so Vn is smaller than the expected offspring, or the surplus of the offspring above 1, then we just observe the classical behavior of Gordon-Watson processes, meaning that the probability of survival is given by Haldane's asymptotics, which is this 2 epsilon n over sigma squared. All right, so far so good. But if the variance and this epsilon n are of the same order and converging to some quantity rho, with rho being between 0 and 2, then we see this phase transition where we really start to pay a price for this random environment. So the probability of survival gets reduced by this additional factor 1 minus rho half. And this is just due to the fact that this extra randomness in the offspring distribution, you start to feel it now, and it becomes harder for you to survive. And okay, maybe not so surprising right now, because if this converges to some rho, which could also be infinity, the process turns out to be no longer supercritical, which is not hard to see. So this is not really a hard statement to prove, and we will see how to do it in a slide. But then the process is in fact subcritical, and the process will die out almost surely for n large enough. And I want to make a short comment, because what is maybe a little bit surprising is that we are comparing the variance to the expectation, and we are not comparing the standard deviation to the expectation. And so because we are dealing with a sequence which is going to 0, the standard deviation is much bigger than the variance, because I'm taking the square root of something small. This means that in a single generation, we will observe subcritical behavior with rather large probability, some real quantity bigger than 0, we will have subcritical generations. But we won't have so many subcritical generations after each other that we really start to feel the subcritical drift. And instead, you can imagine that you need a lot of subcritical generations after each other to really make it die out. And in fact, this is connected. So this comparing the expectation to the variance is connected to this classical stuff. If you have a random walk, in order to have a fluctuation of size n, you have to wait for n squared time. And this is exactly what's behind this statement, that's why this phase transition is at the order of the variance and not at the order of standard deviation. Because I guess you would all agree, if the expectation is larger than the standard deviation, you only see supercritical environments, so this isn't so interesting. Yeah, sure.
So, how should you interpret this probability, this survival probability? It's like a quench quantity with respect to the environment? Or,
this is an yield. It's an yield.
Okay, so this probability is something of the type, so there is an expectation with respect to the environment.
Right, you write this more or less as the expectation of survival given the environment, and then you anneal over the environment. Yeah. Yeah, we can also do a quenched version of this part. Right, yeah, because here the environment doesn't play any role. Yeah. But it's stated in an annealed fashion. All right. So let me shortly mention on the last case, because this is a super easy case. If you are familiar with branching processes in IID random environment, there's this criteria due to Smith and Wilkinson in 1969. And it just states the following: if the expectation of the log of f prime is less than 0, your process is subcritical, meaning that it dies out almost surely. If it's equal to 0, it's critical, and if it's bigger than 0, it's supercritical. So this case C is not a real theorem, I would say. It's just for completeness, you will immediately see that afterwards your process is in fact subcritical. So the C is only, I don't know, more corollary of this result. But we will turn to the proof of part A and B, and they run analogously until some point where we see where we split up from the classical case. So, okay, beware, the next two slides are a little bit lot of formulas, but it's not really hard. So, what you do in the first step is you proceed as for the classical Gordon-Watson process. We condition on the environments being F1 to Fn, and you can express the generating function in generation n in the following way. And as you do it for classical Gordon-Watson process, you iterate this procedure, and normally you would get the nth iteration with the generating function itself, but now we're having different generating functions in each generation. So we iterate different generating functions, but it's a nice and convenient way to write the generating function in the nth generation. And we will introduce this function gkn, which is just starting from generation k to generation n. This is the iterated generating function. And now comes maybe the first, it's also just the same way now. If we want to know what is the probability of survival, we have to evaluate this function as 0. And now, coming back to your question, getting back to the probability of survival, we just take the expectation of 1 minus this generating function evaluated at 0. All right, but now it's the problem. So there are n different functions coming into play to defining this object, how to evaluate this object. And the idea is to introduce another function, which we will call the shape function psi. So this is now without randomness, it's just an object you can define for any generating function. And it's the shape function psi is defined through this formula. And what does it do? It somehow decouples the expectation of your offspring distribution with the variance. So you do an Taylor expansion of this function f around 1, which is the mean. And then everything else, which is connected to the variance, is put into this shape function phi of s. And a good part is the shape function at position 1 exactly states that it is connected to the second moment compared to the first moment. So it somehow decouples the first and the second moment. And what you can do with this is, if you now give me this iteration of ugly looking generating functions, you can do the following. You pull out the first function here. You do this shape function transformation to get the expectation out of it, and you evaluate the shape function at the certain point. All right, and we get the shape function of the first generation. And now we do this all over again, as usual. We do it a second time. We pull out the expectation. We evaluate at this point and get the shape function at this point, but now divided by the expectation, because the expectation is already here. So we are accumulating these expectations over the generations. All right, now I'm doing this n times, and I don't want to show you all n steps, but we will arrive at this formula. So below here, it's just the expectation after n generations. And it's the same stuff here, just the expectation in the kth generation. And we are always evaluating these psi k, these shape functions, at these intermediate points. And now comes a nice simplification. In the end, as you remember, we want to plug in t equals 0. So this t here vanishes, and we're just evaluating at 0. And this allows us, now taking the limit n to infinity, to arrive, not taking the limit n to infinity yet, but plugging in t equals 0 and writing mu n shorthanded for the expectation in generation n. You can arrive at the following formula, and then we can use again the fact that gk plus 1 of n is not a probability to go extinct starting in generation k plus 1. So there's this recursive structure going on, allowing you to transform the probability of survival, now everything working conditionally on the environment, into this really ugly looking formula, I must admit, but we will see in a short while that there's a nice structure behind this formula. Okay, because now what we want to do in the end, we want to see the probability of ultimate survival is we will take the limit little n to infinity to get the probability of ultimate survival or survival forever. And all right, so we obtain the following proposition, which is just a proposition for so Zn is a branching process in IID random environment, and we assume that it is supercritical, and this should be less than infinity, and we also assume that the second moment isn't too large. Then we can express the probability of survival in the following way. So the probability of survival is given as the expectation of 1 over x, where x is just defined as this random sum. And note that before we had this term here in front, but this mu n diverges to plus infinity since we are dealing with a supercritical process. So this vanishes, and then more or less what you have to verify in this proof is that everywhere where here's an n, you can put a plus infinity, which is doable. And important to note for this kind of theorem, it's not important that we are dealing with slightly supercritical processes here. So this proposition holds for any supercritical branching process in IID random environment. And even the IID-ness is not really important. It's only important for us since we are then obtaining some independence in this random variable x. But you can also write it down for some, let's say, stationary environment, or it depends on what you want in the end. But yeah. Of the
like translation in man.
Yeah. Let's say you have an environment f1, f2, fn, and this is a stationary process.
Okay.
For example, this would also work, but I don't know how far you can stretch this statement. All right. So now I don't know if you believe me that we made some progress because we connected now the probability of survival to this expectation. But I mean, the big question now is what to do with this expectation. So there's a lot of terms, and part of the problem about these terms is so these phi k's, they get evaluated at these probabilities of extinction, and these probabilities of extinction they are correlated, because if you imagine you are standing at some time k and k plus 1, and if there's a really bad environment ahead of you, you both are more likely to die out. So that's a problem in this stuff. But we can do a nice and small trick. So this is our x again, and okay, now we're coming to the part where the supercriticality becomes really important. So we let epsilon n tend to 0. And what do we expect? We expect that the probability of extinction should converge to 1, because otherwise, I mean, this seems a little bit strange. And if we just now crudely approximate this probability of extinction being equal to 1, we gain some independence. So we approximate our random variable x, which will give us a probability of survival by this x tilde, which is just given as phi k plus 1 of 1 over this mu k. So I change that. And now this x tilde has a really nice property, being the fact that it fulfills a stochastic recursion. So if I pull out here the first term, which is k equals 0, so mu 0 is 1, so I get this phi of 1. And then I pull out the f prime of 1, so the first expectation out of it, I obtain the same random variable in distribution. And this is a really nice property, because this allows us to study this x tilde. And in fact, I mean, we couldn't use any result which are known, but these kind of equations, so I just rewrote everything. So we are now entering a different world. We're entering the world of financial mathematics, and this equation where y is distributed as a plus by is in a financial context known as the annuity equation. And what does it tell you is you have some asset y, which and we have this interest rate B, which devalues your Y in the next step. So you are losing some money. But on the other hand, you're putting money A in, and the Y is then the value of your asset. And okay, you can think about this without randomness, then it's really easy to solve. But what we are now dealing with is that the input you do into your asset is random, and also the interest rate is also random. And now restating our assumptions means our interest rate B converges to 1. So this is connected to the fact that our process is slightly supercritical, and also the variance of our interest rate converges to 0. So the interest rate converges to 1. And what we will be doing now is study the limiting behavior of Y and properly rescaled. And here we see the same divergence of these cases again, and it's in the following manner. So let us say that the expectation of A is alpha and the variance of A is nice. Then we have this same kind of dichotomy again as before. So if Bn, which is the deviation from 1 of the interest rate now, is larger than the variance gamma n, meaning that this ratio converges to 0, then Y properly rescaled by this factor beta n converges in probability to alpha. So there's no randomness in the limit anymore. On the other hand, if the expectation compared to the variance, and again note we are comparing expectations to variances, converges to some constant C, then gamma n times Y, so we have a different rescaling here. It's asymptotically inverse gamma distributed, all right? It's some distribution with this density here, and we can also identify the parameters. And the proof is not so hard to see where it's coming from, because we can make use of this stochastic relation, and we will work with the Laplace transforms of these. It's just, I will just give you a really short idea how to prove it. And we obtain, if we denote the Laplace transform as L of Y, then you obtain this recursion, this equation for the Laplace transform. And if you now Taylor expand this Laplace transform around lambda, because B is really close to 1, this is what we're expecting, and then we take the limit, we obtain two different limiting differential equations for our Laplace transform. So in the first case, this equation here will converge to this differential equation, which is a super easy differential equation, and it's just solved by this function, and you immediately see, okay, this is the Laplace transform of a direct distributed random variable. And on the other hand, if this converges to some constant C, this corresponds to doing one more step in the Taylor expansion and looking at the second order terms. So this second derivative here pops up, and this differential equation is solved by some modified Bessel function of the first kind, which is not really important. The important stuff is that the Laplace transform of an inverse gamma distribution fulfills the same differential equation. And this allows us to differentiate between the first case, which is classical. So remember, this first case corresponds to classical Gordon-Watson behavior, and the second case corresponds to the random environment behavior. And we see that in the sense that the limit here, the limit is deterministic. So we just converge into a constant, whereas on the other hand, here the limit is now also a random variable. And somehow, in a weird sense, which I cannot really describe well, this inverse gamma distribution, this captures what the environment is doing on your way to fixation, to your way to survival. So this inverse gamma distribution tells you what's happening. But due to this, that we are using all these strange transformations, it's not really sure what this inverse gamma distribution is doing, like how to go from your random environments to this inverse gamma distribution. So, and now the game is just really simple. We just now doing all the step backwards, which we did in the forward way. So we express these pi n as this random formula, as this expectation, which we denoted by x. And okay, I omitted here now a really important part of the proof, and the important part of the proof is that we can really do this approximation. So you have to show in the last step is that this x tilde is really approximating this random variable x well, in the sense that these expectation over 1 over x, they are not so far away. And the idea behind this is it's a rather technical lemmata which involves estimates about the shape functions and seeing how bad it is if I plug in a 1 here, if I have some control about the probability of extinction. And then we can just do our machinery backwards. Okay, we connected everything to x tilde, and for x tilde, we can now use our new theorem about the limit behavior of perpetuities, and we obtain different cases. So again, to remind you, this belongs to the case where we converge to a Dirac distribution in the end, and this corresponds to the inverse gamma distribution. And in the end, this factor here just comes from the expectation of this inverse gamma distribution. And with that, I think I'm done, and thank you for your attention.